The Kepler Space Telescope stopped operating years ago. Its extended mission ended in 2018. Most people assume that means its discoveries are finished. They're not. Last week, astronomers published a new result pulled entirely from archived Kepler data. No new images, no new telescope, just a different way of analyzing something we already had. What they found wasn't obvious, it wasn't flashy, but it quietly changes how we think about finding Earth-sized planets on Earth-like orbits. Let's break it down. Here's what actually happened. Researchers revisited data from Kepler's K2 mission, the extended phase that followed the original survey. While scanning a sun-like star called HD 137010, they noticed something unusual. A single transit, just one event where a planet crossed the face of its star, dimming the light for about 10 hours. That's it. No repeat, no obvious orbital pattern. Normally, one transit isn't enough to say much. Planet discoveries usually rely on multiple crossings to lock in an orbital period. But instead of discarding it, the team looked closer. They analyzed how the shadow moved across the star, how long it lasted, how fast the object must be traveling. Then they compared that motion to orbital models constrained by the star's known mass, radius, and luminosity. From that, they didn't measure an orbital period, they constrained one. The best fit solution points to a planet with a year of roughly 355 days, nearly identical to Earth's. The object was designated HD 137010b. It orbits a star about 146 light-years away. That alone makes it interesting, but the implications go further. This is where the story gets more subtle. Single images can mislead. They freeze geometry, they exaggerate contrast, they invite speculation. But careful analysis does the opposite. It eliminates possibilities. From the depth of the transit, researchers estimated the planet's size, about 0.106 times Earth's radius. That's not a mini Neptune, not a gas-rich super-Earth, just slightly larger than our own planet. That matters because size strongly constrains composition. Then there's the orbit. At its estimated distance, the planet receives about 29% of the energy Earth gets from the Sun. That places it near the outer edge of the habitable zone, not comfortably inside, right near the boundary. Assuming an Earth-like reflectivity and no strong greenhouse effect, surface temperatures would sit around minus 68 degrees Celsius. Colder than Antarctica, colder than Mars. But cold doesn't automatically mean dead. Not yet. Here's where everything hinges. If HD 137010b has a thin atmosphere, like Mars today, it's likely a frozen world, ice-covered, inactive. End of story. But if the atmosphere is thicker, the picture changes. A higher concentration of carbon dioxide could trap heat. A denser atmosphere could redistribute energy. A greenhouse effect could raise surface temperatures significantly. The research team modeled multiple atmospheric scenarios, different compositions, different heat transport assumptions. Their conclusion was deliberately restrained. Depending on how you define habitability, there's roughly a 40 to 51% chance this planet falls within the habitable zone, and roughly the same chance that it doesn't. That uncertainty isn't a flaw. It's the result of narrowing the problem as far as the data allows. They didn't guess, they constrained. Now zoom out. Most Earth-sized planets found near habitable zones orbit red dwarf stars. Small, cool, and extremely common. But red dwarfs come with a problem. Early in their lives, they emit intense high-energy radiation, strong flares, powerful stellar winds. Over billions of years, those forces can strip away planetary atmospheres entirely. HD 137010 isn't a red dwarf. It's a K-dwarf. Cooler than our sun, but far more stable than red dwarfs. Its estimated age is between 4.8 and 10 billion years. Magnetic activity is low. Radiation output is steady. That changes the baseline expectation. If a planet around this star formed with an atmosphere, the star itself isn't working against its survival. Atmospheric retention becomes plausible, not exceptional. That's why this candidate stands out. There's a catch. Everything here comes from a single transit. For a planet with an Earth-like orbit, transits happen once per year. Miss it, and you wait another year. The team hopes TESS might catch another transit. ESA's K-ops is another possibility. If neither sees it, confirmation could take years. Future observatories like the Habitable World Observatory could eventually image the planet directly and probe its atmosphere, but that's not soon. For now, HD 137010b remains a candidate. Not confirmed, not dismissed, just constrained. This discovery highlights something important. Kepler's mission ended years ago, but its data didn't expire. As analysis techniques improve, old observations reveal new signals, especially small ones, especially signals automated pipelines were never designed to catch. HD 137010b likely would have been ignored. One shallow dip, one event, not enough for an algorithm. But treated carefully, that single signal resolved into a testable hypothesis. That's the real story. Not that we found the dramatic new world, but that patient, methodical analysis of existing data still produces meaningful discoveries. From here, it's a waiting game. If a second transit is observed, confirmation becomes possible. Radial velocity measurements could estimate the planet's mass. Spectroscopy could hint at atmospheric composition. If no transit is seen, the hypothesis still stands. It remains falsifiable. HD 137010b could be frozen. It could be temperate. It could have an atmosphere or none at all. What changed is that the possibilities are now narrower than they were before. All from one transit recorded by a retired telescope. That's what 146 light-years really means here. Not just distance, but a dataset, a constraint, a claim that can be tested. A retired mission didn't deliver certainty, it delivered limits. And that's how science actually moves forward. If you want to follow what happens next, subscribe. Let me know in the comments what you think this discovery really represents. I'll see you in the next one.